till the end of this. So my name is Caroline, and my core interest in research are really in finding tools and techniques that help make software more correct, performant, and secure. And as you might guess, right, from this whole conference and why I'm here, over the years, the tool that we've really found to be effective for this is coverage-guided fuzzing. Now, as Kostya mentioned, you've probably heard this mentioned throughout the day today, maybe with some extra adjectives like gray box and mutational. And he had a nice slide that went over the basics of the algorithm. And I'm going to give you another nice slide that goes through this, just so you can map my pictures to the concepts in your brain as I'm talking about them. We call this kind of fuzzing mutational because the way that we create inputs, we start with seed inputs and we mutate them, usually by just flipping bytes, deleting and adding random subsequence of bytes, etc. We call it gray box because usually the programs that we're running are instrumented to collect execution feedback from the executions of the inputs. Oftentimes this is branch coverage, and I'll go into a few different execution feedbacks we can look at in this talk. And we call the whole thing guided by coverage, right? Because the way that we evolve our corpus of inputs through time is we save inputs that actually have interesting feedback, usually meaning that you cover, say, a new branch or a new behavior in the program. And this talk actually kind of dovetails nicely into Kostya's talk, because today I'm going to talk to you about a bunch of projects where we tried to figure out whether we could modify this kind of CGF loop in a strategic way in order to achieve goals of finding different bugs in programs and of this mysterious concept of quote-unquote deeper exploration, which I'll define exactly what I mean by that. And for each of these topics, I'm going to talk to you a little bit about two projects. I'll go through kind of the key research insight behind the project, kind of the key way that you can change the fuzzing loop in order to get different results. And I'll give you like a quick summary of how the software artifacts coming from these projects might be useful to your day-to-day fuzzing lives. So with that in mind, let me get started and talk about, as Kostya guessed, Perf-Fuzz and Fuzz-Factory, finding different bugs in software. So this may have happened to you sometime recently or not so recently, that you were running a piece of software and then in some particular configuration of that piece of software, there was a huge performance impact. And obviously for you as a user, this is not very pleasant. And furthermore, it can be very expensive for your machines. And it can even cause security vulnerabilities because if you have a deployed service, which has a serious performance issue, then an attacker can send a carefully constructed input that causes, all the memory or all the CPU to be used up on that deployed service. You can get a denial of service. Now, because of these problems, there's been a lot of great work into building profiling tools, which if you have one of these like worst case performance inputs, a pathological input to the program, you can pass them through this tool and get a bunch of cool graphs and numbers that a developer can look at to try to improve the performance of the software. This is really great, but it assumes you have one of those bad inputs in the first place, which probably means that something terrible already happened. And our goal in Perf-Fuzz is to automatically generate these pathological inputs so the developer can have a look at them before something terrible already happens. And as you might have guessed, the question we asked here is whether we can use this kind of coverage-guided fuzzing loop, maybe not coverage, just coverage-guided anymore, in order to get this goal. You can think about how you might do this. Maybe the most natural thing is to say, well, hey, instead of looking at the branches covered by an input, maybe we can look at the execution time of an input through a program. And maybe we can save an input if it executes for longer. In practice, this turned out to not quite work for our purposes, because what we were interested in building was really a corpus of inputs showing different bad performance behavior in different parts of the program. And because we kind of wanted to look at algorithmic complexity and execution time at the short times that we were looking at initially with the first inputs you run through your fuzz target, It was just way too noisy of a metric. So what we ended up having to do was something a little more fine-grained. In particular, what we did is we modified the instrumentation of the programs so that what we would get out was a map containing all the edges of the program, of the control flow graph of the program, so like the branches, function calls, and returns, all that fun stuff. And then we kept track of the exact number of times each of those edges was hit, not bucketed or anything, the exact number of times the input hit those edges. And what this enables us to do is save inputs to our seed corpus if it maximizes the hit count for some edge. If you have a branch that's been hit 3 times by all the inputs you've seen before, and you have a new input that hits that branch 4 times or 400 times, in both cases, that's good for us, and we save it to our set of seed corpuses. And it was very important also to modify how we choose inputs to mutate here, right? Because if you have one that hits it four times and one that hits it 400 times, you want to save the input that hits the edge 400 times. Sorry, you want to pick that one for further mutation to try to kind of make progress in this loop. And this actually works in practice. I'll show you some graphs on some relatively smaller benchmarks, but we ran this on a bit more standard fuzzing benchmarks as well. But this experiment is nice because it actually shows us the algorithmic complexity that our tool Perf-Fuzz could find compared to state of the art, which was just trying to maximize the path length through the program alone. So that was kind of a single objective thing, kind of like execution time. So what we did is on these 3 benchmarks, very simple insertion sort, PCRE URL regex benchmark, which is quadratic in the worst case, and a word frequency benchmark, which is a linked list hash table, which is quadratic in the number of words in the worst case. We ran each tool with different maximum input sizes. So on the x-axis here, you have the maximum input size that we allowed each tool to create from 10 to 60. And on the y-axis, we have the maximum path length of an input that each fuzzer generated after timeout. And what you can see is that something very simple like insertion sort, just doing the greedy thing of maximizing path length, performs similar to Perf-Fuzz. Perf-Fuzz is in the blue pluses in this graph here. But on things that are more complicated, like the PCRE benchmark, you can see that Perf-Fuzz achieves a much more quadratic curve than the just single objective approach. And in this word frequency case, it's kind of unclear what's going on here. But if you look at it in detail, you'll find that the prior work, the worst case it could find was just inserting a lot of small words into the linked list hash table because, that causes a lot of inserts. Whereas in our case, we actually found these really cool inputs that were all hash collisions and like forced the program to have to traverse the entire linked list multiple times to insert all these inputs. So that was really cool, really showed us the worst case performance behavior. So Perf-Fuzz is a tool that's built on top of AFL, but the concept can be built into libfuzzer as well. The one thing is it does, of course, require building with a specific LLVM pass in order to get this edge and hit count map. So it doesn't just natively work on, if you have something that's only a binary, we don't out of the box have something that adds that instrumentation to the binary. Now, one thing you might have noticed, or that we noticed while building Perf-Fuzz, is that this algorithm is a lot more general than it's lets on. So although I was talking to you about maximizing the number of hit counts for some edge is kind of the goal of this, in reality, it's kind of agnostic of the fact that the values are, that it's edges and hit counts. It should just work in a case where we want to maximize some sort of key value map of behavior we get out of our fuzzer of our instrumented program. And the neat thing about this is if you have that algorithm that can maximize values for keys, you can solve a lot of other problems. Like if you're really interested in finding bad memory allocation behavior, you can keep track of all the locations where you have memory allocations and the cumulative amount of memory allocated at each of those locations. And then if you try to maximize that, you might find some some terrible memory errors. Or if you have this classic problem that you know, you have a lot of locations in your program where you have these hard comparisons of your input, say X, to a specific value, and it's hard for the fuzzer to come up with that exact value. Well, what you can do is keep track of all those locations and the number of bits matched at each of those locations. And if you maximize the number of bits matched, right, then you're going to be able to have inputs that get through those comparisons. So with that in mind, and the fact that my collaborator and I seem to keep building fuzzers that modified the loop in kind of this manner, we decided to build Fuzz-Factory. And what Fuzz-Factory does is, first of all, it kind of generalizes this algorithm further. You go beyond maximization to this concept of aggregation, which can obviously be minimization or set union. There's some math conditions on that. And kind of the cooler thing about this is something I didn't get into a whole lot of detail in talking about Perf-Fuzz. In Perf-Fuzz, we really assumed that you had built with our instrumentation that gave you this edge and hit count map at this exact location in the instrumentation map. But in Fuzz-Factory, what we do is we really separate the search algorithm that's trying to maximize these key value maps from the domain-specific instrumentation that can be injected into the program to create that maps. And Fuzz-Factory actually provides a bunch of macros which you can either manually insert into your program to basically say, at this location, set this key to this value, and we'll try to do our best to say, maximize the values for that key in the search algorithm. Or of course, you can build, say, LLVM passes that inject those calls automatically, which is what we did in the paper in order to port a bunch of fuzzers. The details of this table aren't really too important, but the point is that we were typically able to do it in much fewer lines of code than if we had created all these fuzzers from scratch, having to build a whole new search algorithm as well as instrumentation. The other cool thing that that enables is that since this algorithm is kind of agnostic of these key value maps, you can kind of just keep throwing more key value maps at it. So it's really easy to compose together instrumentations to get a more powerful fuzzer. This is a graph that shows a bunch of benchmarks. And on the y-axis, it shows the maximal amount of memory that was allocated by an input created during a fuzzing run. Regular AFL is a pale blue bar, which you cannot see anywhere in this graph. The mem feedback I described to you that was just trying to maximize memory allocations is a green bar, which you also cannot see anywhere on this graph. Comp is that feedback that was trying to get through hard comparisons, and you can see it on the libarchive benchmark in the yellow. But the fuzzer that worked the best here in creating these terrible compression errors, decompression errors, was combining together that comparison feedback and that memory maximization feedback. And that allowed us to find these really bad bugs in these programs. The one in libarchive was due to a typo in a macro call, because you shouldn't be getting a 4 GB allocation when you're decoding a 20 byte. So that's Fuzz-Factory in a nutshell. It's again built on top of AFL. Comes with a tool so you can see the domain-specific feedback that your inputs create, kind of bring the human in the loop for the analysis. And you can use the fuzzers we have if one of those interests you, or you can just use those macros to build your own. So for the rest of my talk, I'm going to talk to you about a few projects that are kind of about this quote-unquote deeper exploration. And I agree that the concept of deeper is kind of not super well defined. So let me talk to you about a more specific problem here. So if you look at a lot of the bugs that coverage guide fuzzing finds, you'll find that in programs which have a separate input validation stage, which basically parses the input into a core data structure that is then used by core logic of the program to do, I don't know, something relevant. You'll find that, I mean, maybe someone can argue with me here, but I think that a lot of the bugs that fuzzers find are in this input validation parsing stage. And that's useful. And you'll see that a lot of fuzz drivers that people write that are more unit testy might not even try to get into this core logic. But what I'm interested in is whether we can actually get deeper into that core logic from the entry point that goes through the input validation. And why don't we do that? Well, I think one of the big reasons is because of the ways that we mutate inputs. Right, the ways that we mutate inputs in the standard coverage guide fuzzing is by doing byte flips and really mutations at the byte level. And if you have a program like, say, an XML parser, where you have these hard validation branches, like, for example, you need the tags in your XML document, foo and foo, to match. Well, if you start with a seed input that satisfies that, it's great. But if you're doing mutations at the byte level, you'll find that a lot of the mutants you generate no longer satisfy these hard-to-hit branches in the input validation stage. So you're never going to get deeper into exploring the core logic. This is actually one of my first fuzzing projects where I wondered whether you could do something about this just by kind of adjusting where you are mutating your inputs. The idea of that project, Fair-Fuzz, the core idea of it is this branch mask. Basically, the idea is that you assume you have a target branch that's guiding core logic. In Fair-Fuzz, we use this approximation of branches that are rarely hit, so ones that are hit by very few fuzzer-generated inputs. There may be better approximations for this. And we also assume that we have at least one input that hits that rare or target branch. What Fair-Fuzz does is, during fuzzing, it basically tries to answer this question of where can we mutate this input and still hit that target branch. It does this via some pretty low overhead, just like flip all the bytes and get an approximate idea of which bytes we can still mutate while resulting in mutants that hit the rare branch. And then all further mutations that it creates are only going to touch those bytes which are okay as per the branch mask. So hopefully you have a much higher probability of getting down into the core logic of your program. So basically what we changed in Fair-Fuzz this time is that, again, it's how we select inputs for mutation. We picked inputs that hit a rare branch, hoping that those guided core logic deeper in the execution of the program. And we mutated those inputs with this branch mask. I have some graphs that I ran here before. There were a lot more other fuzzers. And at the time, it seemed that Fair-Fuzz could basically find the upper bounds in terms of coverage compared to a lot of other work. But in particular, where Fair-Fuzz actually performed better was on benchmarks where the complexity of the benchmark really came from a lot of nested conditional structure. So like if statements within if statements or switch cases. For example, in TCP dump, right, you have this packet type, and then depending on the packet type, you have different fields. And that's a case where this masking approach can really help you get deeper into the core logic of your program. Fair-Fuzz is built on top of AFL, because that's what I knew at the time. And I think it has persisted over the years to be used, especially in ensemble fuzzing, because it provides heuristics that are kind of more of a depth-first approach, which can be nice when you're pairing them in parallel with fuzzers that might be more breadth first, because they can exchange inputs with each other. And unlike the ones that tweaked the instrumentation we're getting, this one, if you have something that's compiled with AFL, you can just out of the box run Fair-Fuzz on it, and it works fine. That was kind of one of the goals of this early work. Now, for my last thing, this is going to be very similar to what we've heard about structure-aware fuzzing, but kind of a different abstraction. There's another type of fuzzing, which people don't always call this, but appears naturally everywhere when people are testing complex software, which is that a human writes an input generator, which is basically a non-deterministic function that returns random-looking inputs in a search space. So you get an input generator for XMLs. It might generate inputs that kind of look like valid XML, but they're kind of random. And this is actually very powerful. The reason it might not be more widely used is you need a human to manually write that generator. But it's very powerful because now all your inputs are probably at least semantically valid for your program, unless you have a terrible, terrible generator. And so you have a much higher probability of getting deep into the core logic of your program. But a problem with this generator being kind of a random function is that you don't have a totally nice way to link back execution feedback you might get, like the input you generated passed all the validation steps in your program, or it covered new core logic in your program. Because that generator is kind of just obeying this random number generator to generate its inputs, you don't really have any way to tell it was doing a good job. So we had this observation, which again, I think has showed up in some other structure-aware fuzzing work, that although this generator is written with these calls to like random.nextInt and random.nextString, what's actually influencing what integer or string is being returned is the random number sequence that the random number generator is generating. In reality, you can view that sequence of random numbers as a stream of bits, right? So you can view that this generator is massaging the stream of bit parameters into a highly structured input via its various calls to random and the internal logic in the generator itself. So this observation led us to create JQF, which is a framework for generator guide-based fuzzing. And basically the idea is you get feedback from the program under test, and then you can guide the random bit parameters you're getting from the generator. And the cool thing that this enables is that actually when you mutate those bits that affect the decisions of the generator, you're going to get a different path through the generator, and you're going to get a different structured input. But depending on the mutations on the bits, that structured input might actually kind of be a mutation of the input that the generator used to generate. So in a way, you kind of get structured mutations for free. So it's a little subtle, so feel free to ask me questions about that later if it's not clear. I want to talk more about the framework just in my final minute here. You can put in a lot of things into this backend that controls the bytes. You can do regular like AFL fuzzing. You can do a fuzzing that really focuses on generating semantic inputs in Zest, plug in Perf-Fuzz there. We have some recent work that focuses actually on trying to use reinforcement learning to generate a lot of semantically valid inputs quickly. I'm happy to talk more about that offline. Just to give you a sense of what you can do with JQF, it's actually a Java framework. You annotate these JUnit methods with @fuzz. If you have an input stream as your input, then you can just do regular, AFL coverage guide fuzzing. You can also @fuzz things that take in collections or things you write in custom generators for. In this case, there's a built-in generator for maps and strings. So you could just say @fuzz, and then semantic fuzzing with Zest tries to generate more and more inputs which hit that pass that assume statement that are semantically valid for this test. And this framework has been used quite widely. It is a Java fuzzer, but I'm really excited to see these concepts applied in other places, and it's found a lot of nice bugs in pretty robust pieces of Java software. So that's all the time I had. Thank you for listening, and I'll take any questions. Oh, what I mean by ensemble fuzzing is instead of just running a single fuzzer, it's a great question, instead of just writing a single fuzzer that's doing its very, very best to explore the program, you say different fuzzers are good at different things. I will run 5 fuzzers at the same time and have them all exchange inputs with each other. That's kind of what I meant by ensemble fuzzing.
Okay, I think that made it clear. So another question is, although you favored LLVM for this approach, is there a reason you couldn't get the edge hit count for a GCC approach?
No, I'm pretty sure you could do that. It's just that the tools that we were best at in my group was doing was in creating LLVM instrumentation passes. It's what we were familiar with, so that's what we did. But conceptually, I'm pretty sure you could do the same with a binary instrumentation approach.
All right, and then there's another question concerning the combination of fuzzers with symbolic code execution. So would combining Fair-Fuzz with symbolic code execution make sense? Or does Fair-Fuzz get deep enough as it is?
Fair-Fuzz does not get deep enough as it is, right? It can get through, it's like very good in these cases where this masking actually gives you like the structure of the input. But for example, in the XML case, right, you would fix all the tags that have to be the same, while actually you can mutate inputs can, those tags can be different as long as, you know, they're, the left and the right ones are the same. So that's why I said it is probably more scalable than symbolic execution, but it definitely could benefit from being thrown a few inputs that a symbolic execution engine can edit, can create that hit a rare branch, and then it can use that input it'll try to mutate those a little more smartly and maybe faster than the symbolic execution engine could.
Okay, one last question. Might Fuzz-Factory be integrated into AFL++ at some point?
That's a good question. I mean, I'm not the AFL++ guys. The code changes are not too bad, but it does mean you have a different way of picking inputs for mutation, because you want to pick ones that, you know, add to your feedback. So maybe this is something for further discussion in the development of AFL++.
Okay, right. Thank you, Caroline, for being the last highlight of our conference. Okay, which was not completely right because we have another talk, but you were one of the highlights of the conference, definitely. And yeah, it was great to listen to you. And now we come to our open Q&A session, and I'm sure Caroline is also happy to answer questions in the Slack channel if you have more questions for Caroline.
Thank you.
Bye.